welcome everyone, and thank you so much to our speaker for the evening, Renard Di Francesco, who is Director Europe of Standards of Technology and Standards at Sony, and has held this post for well over 20 years now. I'll just give a little bit of background to Renard, and then he can begin his talk. He is a graduate of the École Polytechnique Paris and the Telecom Paris Tech, where he completed his PhD. He's had a very long and successful career, beginning as a semiconductor engineer for AT&T. And would it be fair to say, Renard, the focus has really been on research and standards development for yourself? I think that would be fair to say that is correct. And you are the Sony representative on the international standards bodies for artificial intelligence and the Internet of Things, and also a fellow of the Institute of Engineering Technology, and we're very pleased to say, has now joined the BCS and is working with us at the FACS group. So that's really great. He's the author of numerous papers and books and things, and his research interests include agent-based modeling of pandemic propagation in defined context, and most recently, matrices of sets, which is what we're going to be hearing about this evening. So, is there anything else to say? I'll hand over to Renard.
Thank you very much, Keith, and thank you very much, Jonathan, to host me tonight. And this is my first presentation at the BCS and within the group of formal aspects of computing science. So I have prepared a presentation in which I will I'm not sure if, can you see the slides?
Yep. Yeah, see that fine.
Okay. I will start by introducing the nature and structure of the matrices of sets. I will say a few words about their origin and provenance in the referring to other disciplines of applied mathematics. And then we'll go through a few illustrations of operations with matrices of sets, and then potential use cases, and a first use case is explored as well, and the next steps, because I have the feeling that with matrices of sets, it's just starting, and there is a lot more which can be done, and which I, as a single researcher, will never be able to do. First, because I have limited mathematical abilities, and second, because it's the amount of time and effort is beyond one person. So first, matrices of sets. So we have a matrix structure. So Mij. So we have lines and columns. So we form a table of numbers, and with that, matrices are now ubiquitous in any science, not only hardcore sciences like physics, but also in social sciences. In anything where you record data, you have matrices, and the data availability in computing or through computing has increased, and there is an appetite for data based modeling, and therefore an increased use of matrices. But those matrices are usually a table of numbers and not tables of sets, which is now the topic of the talk. So now the sets are interesting in that they describe whatever is needed. Of course, they may not be always as efficient as a vectorized representation of phenomena. In the introductory session, we heard from the Met Office that fluid mechanics is a main computer of a main consumer of computing capabilities because of fluid mechanics. In fluid mechanics, you have the possibility to have regular models, and they are very complex, but you know what you model, or you try to know what you model. It's not always possible to put things into vectors. It's mostly possible in most cases to have sets. So that's why it's interesting to introduce the notion of sets and open the field to a wider possibility than just having vectors. And numbers to compute are very efficient. They are just a summary of things. And I'd like to show you on the left-hand side of my screen where matrices of sets can be made to appear. I'd like to recall the old legend from India, which was also found in some version in Arabic, from the chess player or the chess inventors, depending on the version, who was teaching a ruler or a prince or a king to play chess. And the king was so pleased that he said to the chess player, please ask whatever you want, and I will make an effort to give you that present. And so the chess player, who was also very clever, said, I put one grain of rice on the first square of the chessboard, and then I put twice more on the second one, and twice more on the third one, etc. So I get to 2 to the power of 63 because I've started with 2 to the power of 0 on the last square of the chessboard. And the total of this is probably more than the total rice production of the kingdom, and therefore that was an amazingly high number or request. So physically, imagine this. On the other side, you have a matrix of number representing the number of grains of rices. So you have 2 to the power 0, and the end is 2 to the power of 63. In between, you can have a matrix of sets where at line I and column J, you have M of ij, which is a set where you have indexed all your rice grains, giving them an individual feature. So imagine you do that with industrial products. You have a barcode, a single identifier per product. So this is what we do with matrices of sets. So this is something which is a summary of the world, which is more comprehensive than the summary of the world with numbers. Now we'll see something interesting later. It's that actually the theory of sets was devised to model numbers, sets of numbers. So in fact, the two are not completely disjoint. Now, matrices earlier than computers were invented in this beautiful country with Arthur Cayley in 1858 publishing a memoir on the theory of matrices. That's really where the world is coined and where the concept is explained in its current form. Actually, all these articles, all these references here, you can read them today, and you have to make no special effort to understand them, because they speak exactly the same language of mathematics as the one we speak today. This is recent history. This is not Newton, this is not Leibniz, this is not Descartes. Reading Newton, Leibniz, Descartes is a bit more tricky, because the way they express the concept is a bit old-fashioned, whereas this is, let's say, modern mathematics. And so Jordan is famous for the Jordanization, which is a reduction method in matrices. And you have also contribution by David Hilbert, who formalized a number of problems in mathematics, including the integral equations, and he used matrices, he used other tools, more basic, more deeper rooted in mathematics. And here I found a reference to a 1930 radio speech by David Hilbert, but his production on matrices is probably 1904, 1924. Georg Cantor, in two times, 1874, a paper on the properties of the real numbers. And this property leads him to define the sets, because to formalize probably a problem on numbers, he creates the sets. And today we know the sets. And the set is a final touch was brought by Cantor in 1895. I read this document and I could understand it. It was very easy to understand it. It was exactly the same way we are taught about sets. And in the French case, in my generation, we learned about sets when we were 11 years old. And we learned about matrices the year of the A levels and the first year of university. And you worked during the two first years of university on refined things here. So I have to apologize, because what I am explaining today is something it took me 40 years to realize it was possible. So I'm very slow. Apologies. Because for me, that's things I learned 40 years ago. And putting the two together is something which I have dared to do only this year. And therefore, I'm a bit ashamed to have waited so long. Conversely, I would have loved to hear about the combination of the two models or theories when I was at school, but it was not done. So what can we do with matrices? We can do a matrix product, which expresses as line column. So scalar product of a line vector with a column vector. So we have matrix M multiplied by matrix M prime. And this is M, the sum on K's of the MIK M prime KJ. So nothing particular. Just that we do these computations and we love it when some simplification occurs. Because there is complexity, and in computer science and in any engineering, we love simplifications coming from the structure of the data we use. And therefore, that's interesting. We have lots of simplifications here. And we will show that going to the matrices of sets, we have similar simplifications expressed in different ways, however. So what we could do with sets, we can define a product, but that's the Cartesian product. I take an element in MIK and an element in MKG, and I combine them as A, B, and I have A, B between parentheses. That's my basic tool here, my basic result, whereas here it's the product of two numbers and therefore it's a number. So when I say number, it can be anything in a ring, in a field, in an algebraic structure. So here there are sets. What can we do? The equivalent of the sum of sets can be seen as the union of the sets. This can be discussed. A friend of mine who is a specialist of formal computing told me, yeah, union, yeah, I prefer a special union, which is the square reunion symbol, where we do not discard intersections. We consider the replica as non-intersecting, actually like industrial product with the serial numbers. You never have twice the same. I do like the idea that I perform the reunion of sets, and therefore I stick to that definition. And from there, you will see there is a model. You could do another theory, and with this reunion of distinct sets. Okay. Something which we note is that for numbers, you have a product is zero if and only if one of the two members or terms of the product is zero. In the case of sets, it's about void. So and we have the same property. Actually, you can verify it for yourself. Okay, now when we move from matrix to matrices of sets, we move from linear spaces with vectors, scalar products, addition of vectors, subtraction of vectors, and multiplication by matrices to something which is much more scary. You do not have the comfort of linear spaces in sets. And you do not have the comfort of even multiplying by a scalar, because what would that mean? I have to define it, and then I'm back to number, and I said I was in sets and there were no numbers necessarily, so I would have stronger hypothesis. So the way around, which I found after weeks of not finding again to find something, it's some people it comes very quickly. For me it took me a bit longer. In fact, v, so the multiplication of the matrix with a vector, equals lambda v in eigenvalue eigenvector case. You can modify it by saying it is a matrix with lambda on the diagonal and 0 elsewhere, multiplied by v. So because you do lambda v1, lambda v2, lambda v3, etc. for all coordinates of the vector. So it's exactly this. And the meaning of this and the meaning of this are totally equivalent. Therefore, why not try, in the case of matrices of set, to use this, which is more generic, in fact, than this, because we do not assume the existence of a scalar product. We just replicate a generic set, say lambda, along the diagonal, and we put the void set, the empty set, everywhere else in the matrix. So MV equals identity of lambda, the diagonal of lambda multiplied by V. That's the equivalent problem of the eigenvector eigenvalue. And I note that in English, the German words were taken. In French, we took the liberty to have our own vector propre and valeur propre. And so that's a mathematical difference in the expression. And so we have that. Trying to solve a few problems of that kind. So let me illustrate how it works for you to have a direct feel of how matrices of set can work. I take a 2-2 case, a matrix which has 4 elements, so one line of 2 and the second line of 2 and a void or empty set here to have less computations to make. And I multiply this matrix by a vector of sets. So coordinate 1 is a set X, coordinate 2 is a set Y. I multiply line by column, and that gives me A, X, B, oops, sorry, shouldn't click. Here. So A, X, B, Y. And the plus is not a plus, it's a reunion. A Cartesian product X union B Cartesian product Y equal this lambda V first coordinate of v, which is x, so lambda x. And the second one is easier, so void x, that's void, and cy, that's just cy, equals lambda y. So if y is not void, not empty, then c equals lambda. And then the condition 1 is an equality, but the reunion of two sets equal another set imposes that this subset of the reunion is a subset of lambda x. So I write it here and the same here. Therefore, I get the three inclusions: B included in lambda, A included in lambda, Y included in X. And because, let me start with this, from Y included in X, and lambda X equals this, which is from here, we get Y in X. We replace here, Y is in X, so B Y is included in BX, and therefore this set, lambda X, is included in A union B Cartesian product X. So we see it's very elementary. And therefore you have lambda included in A union B. And now I go back to this, B including lambda, A including lambda, and this imposes the reversed inclusion. A and B being in lambda, the union of A and B is also in lambda. And therefore with 2 and 3, we have then equality. Now we can decompose the set X, which contains Y, into Y and its complement in X. Let's call it T. So we have a decomposition of the elements of X into those in Y and the others, which are in T. And the intersection is void. Then we transform 1 into AX union BY, A union BY, union AT. And therefore we have this lambda, yes, because A union B equals lambda, we've seen it here, we replace it, we have lambda Y union AT. And with A union B equals lambda, and therefore, sorry, I was starting from here. I replaced X as Y union T. X is Y union T, and therefore I have this. And on the other side, I have A union B, which is lambda, and I have AT. So I just leave it that way. And now I project onto T, because then this Y and T are disjunct. Therefore, I can keep the component with T, the couples of elements of lambda times T, and the couples of elements from A and T, and there is identity between the two. And therefore, we have lambda equals A, and B is included in A, because we have this here. And therefore, we have a theorem, which is B here, included in A equals lambda. That's the hypothesis here. If we have that, if we have Y included in X, then we have this equation. And therefore, we have V eigenvector and lambda eigenvalue. So this is a first spectral theorem, of course, in a simple case. But you see, that sort of result can be expected with matrices of sets. So anyone can do that. And I suppose it's A-level mathematics, and therefore not very tricky to make. Just you have to follow the steps one after the other, and that's it. Now you can establish a generalization of this theorem, which is not very difficult to establish. You take a matrix which has lambda on the diagonal, the same set, and you have above the diagonal or under the diagonal, as you like, you have empty sets. And you have a vector where the coordinates are included into the next one. So V1 included into V2, included, etc., into Vn. Therefore, I multiply line by column. I get lambda V1 here. Here I have two terms. I have E21 V1, lambda V2, etc. And you will quickly verify that we have, in fact, an eigenvector, because we get matrix applied to V equals lambda, diagonal of lambda applied to V. So we have the eigenvector, eigenvalue condition satisfied. And this is just one particular case of eigenvector, eigenvalue solution. So you have many more, and here a very simple one. If you have a constant sum line, that is in set terms, it's union on the car, you take the line of the matrix, of the set matrix is AI, AI1, AI2, etc. And you do the reunion of these. And if this is constant, equal to a lambda, independent on I, and if you take a vector which has all identical coordinates, it's easy to multiply lines by column, and you will get a factorization of this W. So you get the union of AIK multiplied by W equals lambda W. And that's very easy to prove, but quite interesting result, because we see that the eigenvalue, eigenvector works in a very different way with sets than it works with classical matrices. This one is a funny one. So imagine you have a matrix with on a certain line and on a certain column, you have the inclusion of each term into the next one on the line. So I call it Matryoshka because this is the Russian dolls, which contain the preceding one, the smaller one. And we do the same in column. So if I multiply one line with this property with one column with the same property, that the last term is the bigger one containing the other, then this this is an index. Sorry, it shouldn't be big K, it's K, small kj. But this term is included in the last one of the line multiplied by the last one of the column, those two larger Matryoshka. So we have a very interesting simplification. In large data sets and large computations, we are always looking for ways to avoid repeating tedious computations, and therefore this is a welcome simplification. Now this can be generalized. Of course, the Matryoshka, the big one, can be anywhere along the line, and if we are lucky enough and the same property is true within the column with the same index, so here I say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, then they will hit each other and they will contain all the other terms of the reunion. And therefore, we just keep those two big ones because they contain all the other. So we don't need to keep all the others. Just this one is the result of the computation. So we use the inclusion of sets in a very efficient way. This leads us to another topic, which is polynomials. So if you have numbers, the possibility to multiply numbers, you can build polynomials, and polynomials are mute letters which you can replace with whatever you can raise to the power k. So for instance, a classical matrix M can be raised to the power k because you can multiply M by itself k times. And therefore you can, from this polynomial classically defined for numbers, I can put 2 instead of x, and there I would have 2 to the power k. I can put instead a matrix, any matrix of number, square matrix, and then I have this. What do I do for matrices of sets? I have a problem first. I do not have the possibility to multiply by a scalar, by a number. So I have to find another way. I can always multiply by a matrix, another matrix. Now, if the result is to be sets, I want to have physical homogeneity. And it's interesting because a previous talk at the same series of seminars, which is BCS, Formal Aspects of Computing Science, has been on the physical dimensionality, getting the dimensionality right in computations. And this is exactly the case here. I want to multiply a matrix by another matrix, but to do this sum or a reunion, I need to be operating in the same set. So I need the combined dimensionality of all these terms to be exactly the same, because I want to perform a reunion of sets and be comfortable about that. So multiply by AK, sorry, we translate it into set matrix multiplied by 1 of AK, the diagonal matrix formed of AK replicated along the diagonal and the empty set everywhere else. And we want the dimensionality to be right. The highest degree is called D. So in our case, we will have to face matrix M to the power D, and we will have to multiply it by 1 of AD as a diagonal matrix formed of AD replicated. And therefore, we will need, in the product, we will need the dimensionality to be right. So we have a degree D here. We assume that M have terms in E, so M to the power D has terms in E to the power D, and therefore we need to have the coefficient equivalent, the matrix here, to have a dimensionality, let's say, in E. So if AD is in E, and if each AK is in ED plus 1 minus K, because we'll multiply it by K, then we will have everything, every member of the reunion there in the same set E to the power D plus 1. Therefore, we are comfortable doing a reunion. And therefore, P of M can be defined as union from K equals 0 to D of 1 of AK, the matrix, coefficient matrix, multiplied by MK. And here we compensate the variation of the dimensionality here by an increased or decreased dimensionality here. As in, if in physics, when you have force equals mass multiplied by acceleration. So you want to have the dimensionality right in here. It's exactly what we are doing. Now, a very specific case. Imagine we know of a vector V which has eigenvalue, eigenvector property with an eigenvalue set lambda. Therefore, we have M applied to V equals 1 of lambda applies to V, and we can replace, we can use this property here by doing P of M applied to V, and we observe that P of M applied to V is simply MK applied to V here. And since MK applied to V is easy to see that it's 1 of lambda to the power K, and we combine the two. Of course, diagonal matrices, it's very easy to use, even as matrices of sets, and therefore we have this property. So we have a very easy computation in the case of eigenvalue eigenvectors. I have tried to explore a bit further than polynomials, for instance, the exponential, which is a series, infinite series, sum from 0 to infinite of x to the power k divided by factorial k. And it's a bit tricky. So I'm not presenting anything on the topic here, but if you are interested, we can discuss later. It's a bit thought-provoking more than a strong and absolute result. But my claim is that we can do some anonymization of data, of the data which is carried by a matrix of sets. And let me give an example. So we have a matrix of sets D containing data which is Dij, with I being a person, J being another person. The link between the two persons is a set which is D indexed by Ij. And we want to anonymize it to satisfy GDPR or more general privacy protection constraints and objectives. We define a matrix formed of columns of sets. So lambda 1, lambda 1, lambda 1, lambda 1 repeated, lambda 2, lambda 2, lambda 2 repeated, etc. Lambda m, lambda m, lambda m repeated. So it's a matrix of sets with very straightforward columns. I call it K, and I will multiply D by K. So when I multiply D by K, I have Cij, which is by definition of the multiplication of matrices, union on K of Dik multiplied by lambda j, lambda kj, but this is constant and this is column j, and every coordinate is equal to lambda j. So therefore it's this expression. And therefore I have this possibility to, the parentheses can come here. And now I continue and I multiply the result of this computation by KT transpose. And in that, doing that is very easy. So I call it D prime. So this is lambda I multiplied by CKJ with a reunion on the two. And therefore I expand CKJ using this, changing a bit the indices for not to get lost. So D prime Ij is lambda I multiplied by an expression which is dkm, union on k and m. And this expression is multiplied on the right-hand side by lambda j. And here we have an anonymized version of the personal data Dij. So we don't know which k, which m owns this particular part of the reunion. This is an anonymization, actually. So a bit trivial, but it works. So the way I came to this, let me be honest, I did it in dimension 2, and then I found that it worked, and then I observed that maybe it would work in dimension n, and actually it works in dimension n. Now I don't want to be too heavily footed on the math, and therefore I'd like to go a bit more towards the use of matrices of sets. Now I hope I have illustrated here and there how it works. Now it's time to see, well, what can we do with it? My method for looking for use possibilities of matrices of sets, I'm an engineer, so I tend to like when a method is used for a particular application of interest. So I've looked for when classical matrices are used, with classical models of matrices. Typically, a vector is multiplied by a matrix and or by a number of matrices, and this is because of the structure of the problem. And then it determines the linear model or the partially linear model, etc. And instead, can we replace a classical matrix and generalize by a matrix of set? And that's the question asked. And I've tried a bit of everything, and I found a few interesting things. But maybe before I go into more detail, I should also be honest. The first time I came across matrices of sets was when I was asking, let me go back to my first slide here, maybe. So I was asking myself, I have a graph which has edges I indexed by I and j, and vertices in ij, the description of the graph is usually very, very synthetic. It just says you can go from I to j. That is, there is an edge going from I to j, and no other information is given. And in the real world, when you want to cycle from one place to another, when you want to walk from one place to another, you need to have a bit more information about the way, the path. So my missing object in the graph theory was a description of the path, the detailed description of the path from I to j. So what they call adjacency matrix, which looks at the summits or vertices of a graph and how they connect to each other, if they do. Then you form a matrix and you put a 0 if there is no connection, and you put either 1 or the number of connections if you have multiple paths, depending on your model. And this is what is called an adjacency matrix. This is a very slim structure and not enough for me, because I wanted to have more details on how you go from I to j. Which street, is it a comfortable street? Is it, does it have a slope? Does it have often traffic jams? And what's the likely temperature in summer or in winter, and so on? Some things like this, which were not described. And I was wondering how to do it. And therefore I tried to define these sets as being the container of that information, of the path between I and j. In other terms, the description of a path from I to J. And the product of matrices in that case is the concatenation of a path from I to J or I to K to from a path from K to J. So I to K is formed in the matrix product by I, K, K to J. And you see this appearing just in a particular case of concatenation of path. But then if you try to look at how things work, actually, you don't need to make the assumption of the graph anymore. And you have the matrices of sets, which have their life of their own. So now it's time to go back to routing using graphs, which is really what I had been trying to do. And I was lucky to find on my way Jaoud Boukashour, Amina El Yagoubi, and Mohamed Charbili from Université de Le Havre, Normandy, who are specialists of multimodal transports. And we have published an article from the conference of the International Association of Maritime Economists. This conference will happen in Rotterdam in November. And another category of application from I to J is from a product J to a consumer I. So you might have MIJ describing the relationship of A to J, and a number of other applications we will discuss if we have time later on. So basically, in very short, my big enemy in economics is the utility function. And I'm not the only one to consider that the utility function is a cloud of smoke of the economists. It has no unit relevant. It has no, it's just a convenient way for them to order preferences and to give them scores. But in reality, it's much better to use the real baskets, the sets, and compare the preference of sets. It's what people do in real economy. So that's what we have tried to do in particular in those economics models. Probably a more important and more fruitful case is collaborative filtering. Many of you are familiar with collaborative filtering. So I'll just recall that this is used by companies like Amazon or eBay to say, if someone has, if you are looking for a product, we recommend you to people who have looked at this product, have also looked at this other one. And this is the recommendation tool with huge business impact for those online suppliers. So it relies on business and social network knowledge on people, how people react to product, service, or a stimulus. And therefore, you put a line per user and a column per product. And so you have user 1 with product 1, but you have user n with product 1. And you look in your matrix, you look at similarities across users, and you find for a certain user I, you find his or her neighbor, people with similar reactions. And based on this, you recommend products which I has not looked at, but the other people in the set of neighbors have looked at. And doing that, you have classically only matrices of numbers. But what we do is richer information. In the reaction of user I to product, we can put their comments, we can put the stars they put on the different products, we can put the mood in which they were when looking at the product and so on. So we can have a lot more metadata and data in a set packaged in an informal way, heterogeneous way, and possibly what you get for user 1 and what you get for user 10 will be heterogeneous, and as in real life, you don't get the people to be vectors. They behave differently, and you have different information from them or on them. The second matrix is looking at similarities between the different products. So I and J, you compare one product with another one, and usually you put a score. They are close, they are correlated or not. And that's very rough information. What we offer with the matrices of set, we can package a lot more information on these two products have something in common, which is unique. And it could be heterogeneous information. And the comparison of I and J might be different from the comparison of I and J prime. And then because you have different information sets, and as in real life. So then the recommendation can be to build on surprise or to build on comfort. And you do what I have explained earlier. You look at neighboring users with similar behaviors, and you extract from those behaviors either the most extreme, which will lead to surprise, or the most average, which will lead to comfort and boring. And usually collaborative filtering leads to boring. It's not for me to try to remove the boring dimension of recommendations engines. What is also interesting, looking at collaborative filtering and how it works, drug target identification uses similar algorithms. It uses the comparison of proteins and use cases of solving pathologies and similarities across the different target drugs, and therefore it makes recommendation. When you look for a new drug, you start from existing drugs in a similar way that you do recommendations here. So this is of course much more important for mankind, and therefore that's interesting. Both of them are linked mathematically, but probably this is more critical. So with that, I would like to just check the time, yes, to introduce you two next steps, which I would like to investigate. Not necessarily, it's not necessarily a task for me, but anyone interested might want to have a look. I have not had any time yet to devote to Gram-Schmidt matrices of sets. In the classical case, Gram-Schmidt matrix is a matrix where every term, Gij, is the scalar product of two vectors, xi, xj. You have a different version, which is mathematical expectation of xi, xj. So instead of the scalar product, because you introduce a stochastic dimension, and these are probabilistic vectors, and this is correlations. And in the case of matrices of sets, using the tool and framework I have developed, you reach this point. This is a Cartesian product and its reunion, and therefore what can we say about it? When does it simplify? Does it have eigenvalue, eigenvectors? We know an interesting property of Gram-Schmidt matrices in the classical case is that they are diagonalized and that they have positive eigenvalues. Yeah, to be studied. And by the way, doing some research on Gram-Schmidt, Gram, a Danish mathematician, and Schmidt. But the problem with that, the mathematical community calls it Gram-Schmidt. but it's mid-18th century, and so 1850s, something like that. Whereas much earlier, Laplace and another mathematician, I think Cauchy, had found independently the properties of these matrices, but the name is Gram-Schmidt, but the inventors are earlier. Here, maybe a more, so this is classical things and worthwhile investigating. So if we want to go a bit further, maybe we will look as well as the shifted versions and the convolutions of sets. That could be very interesting, because in signal processing with convolutions, you have a lot of systems well represented, and therefore input output, and the output is a convolution by the by a function which is characteristic of the system, and that could be interesting. Now, maybe more challenging, but more puzzling as well, and quite interesting, L-sets. So the problem of matrices of sets, as here, is every time you multiply, the reunion adds new elements. And therefore, unless you have void sets or sets which are included into one another, as in the Matryoshka case, this is growing, this is inflating, this is a balloon growing, inflating, 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 and never decreasing. There is no decreasing mechanism linked to matrix multiplication here. Whereas in the classical matrix set, you have a decrease, which is possible because you have negative numbers balancing positive numbers. So how do you introduce negative sets? Well, someone, a professor of Bordeaux University in 1992, has published a very interesting article, Loeb, and I call it L-set because of him. He has introduced sets with positive number of elements and negative number of elements, and he has not explained in concrete terms why he's done it. He has done it for mathematical reasons. I prefer, as an engineer, to have some concrete explanation why it works and how it could work, how we could visualize it. So I would say you have the sets of what we have, an inventory of our possessions, and this is a classical set. So I put the accolade and I put A, B, C, etc., all the elements which I have in my possession. Now, there may be another type of set, the set of what I do not have and which I need and which I want. So the shopping list. The shopping list is what I do not have. And the content of my fridge is what I have. And when I bring back home the content of the fridge, it compensates the shopping list. But as long as I have not done the shopping, I need to do the shopping. So this is open. And this is open in a negative way. I need it. And to close it, to reconcile the two, I do my shopping and I compare the two. And then this is what accountants do, but they do it with numbers. You have your revenue and you have your debt. And what we do here is we create revenue sets and debt sets. And that's something which helps. So looking at the time, I think I should stop here. First, to thank everyone, the attendees, you, and also to think back of the earlier listeners who have helped me refine the framework for matrices of sets. On the 4th of March of this year, I had the honor and privilege to be listened to by Keith Lines and some of his colleagues at NPL, the National Physics Laboratory. Then in April, I discussed with and presented to Université Le Havre Normandie, and a cooperation on multimodal container transport resulted from that. On the 19th of April, I discussed with the Université Gustave Eiffel near Paris, and their interest is in geographic information analysis and visualization, and matrices of sets are candidates to help them. Coventry University on the 6th of May, and a general interest in this new model yet to be analyzed further. And I thank you very much, Jonathan Bowen and Keith Lines, for making this seminar possible. Now I'm listening to questions, if any, questions and remarks.
Okay, well, thank you very much, Renaud. That was absolutely excellent. So much to think about there. So as you say, we've reached the part of the evening where Renaud will take some questions. If you want to put them in the chat, or at least put the fact that you would like to ask a question in the chat, and then I will ask you to unmute yourself should you wish to ask in person. And of course, we are still recording this for the moment. But what I'm going to do is I'm going to take co-chair's privilege and perhaps ask the first question, Renaud, is thinking about the standardization process has obviously been a very important part of what you've been working on over the years, and the formal aspects. Because in the early 90s, there was an initiative, an effort to really sort of start using formal aspects more within the standardization process. For example, in the things like the specification of communications protocols.
Yes.
Do you see any crossover in these two aspects of your work, and how the formal aspects can be helpful in the standardization process, such as, for example, the matrices of sets?
In short, I've looked at bottom up at containers at sea. And containers at sea, in a way, there is a standardization of their indexation, of their barcodes, of the way their content is described. And that would be a pedestrian approach to a matrix of set, a first one. Another one is a bit more higher level. There is a strong interest now in the digital twins.
Oh, yeah.
And in the standardization of digital twins, which is happening at the ISO IEC JTC1 SC41 committee, which is handling both the Internet of Things on one side and the digital twin on the other. There is an overlap between Internet of Things and digital twins, but the digital twin is not only Internet of Things. So when you want to represent a system with data, with codes, with a replication of an executable code, executing in real time a replica or replicas of the real system, you might have the use for matrices of sets.
Yes, it's very, very interesting, because I don't know whether or not the complexities that need to be overcome in the use of these methods, let's think about that, can be some sort of a barrier to their use more generally in standards. Do you have any thoughts about that? Or because you know, these subjects take time to study and learn, obviously.
Yes, yes. Yes, in fact, the current framework defined needs to find a very precise application in a sector, and then I I'm more hopeful of a practical standardization.
Yeah, so it's just a matter of finding the right example.
Yes, I think so, and maybe I could illustrate in more depth. So maybe you see containers in a harbor, matrices of sets. The container itself can be mapped into a matrix of set, and you can form a matrix of sets, which is the piling up of the containers in the harbor. And it's crucial to the logistics efficiency that the container is placed in an optimized fashion, so that you don't have to dig very deep to find the container, and you have to minimize the Rubik's cube transformation.
or the game of Jenga.
Yeah, and some people work on that, like Yashba Khadija. She's from the University of Oran, and whereas for the routing of containers between harbors and over multiple transport ways, including rail and waterways, inland waterways, these people have done critical research on the topic. And that's very interesting because it's practical, but it's mathematical, it's computing. It's quite interesting. And here, geography is never far, because we have the natural, well, we find the graphs, we find the path between I and J, and the flux between two countries, the flux between two locations. These people, they tend to use many matrices of numbers, and every time they speak of a feature, they create a new matrix. So it's unstructured. Whereas with a matrix of set, you might have a way to structure their information, their heterogeneous information, in a more hierarchical way. So that's a possibility. So here, many different matrices replaced by a larger matrix of set. That could be one possibility. That's yeah,
an excellent way of explaining the concept as well, with the containers and everything. That's really good. That's really good. Almost work the opposite way, and it's an excellent way of introducing the concept.
Yes. Yes. Yeah.
Question for Ashok. Yes, the recording of this webinar will be up on the BCS YouTube channel. Jonathan, is there going to be any links to that from the FACS
Yes,
website?
It'll be linked from the page on this talk. So if you go to that, I don't know when it will be put up. That's up to the BCS, but perhaps by a week's time. They normally edit it and so on. But that's where it'll be linked.
Okay. Is there any other points? Anything anyone else would like to raise? Please feel free to do so.
Well, I'd be interested to know, the tool support with things like Mathematica or MATLAB. I mean, have you done anything with those tools, or is it easy to produce a library to help you use these matrices of sets and so on?
That's an excellent question. For now, it's a one-man show. I have focused on the algorithms, on the applications, high-level modeling. But no, I do not have an answer. However, my colleagues from this Université Le Havre Normandie, and namely, I'll be more specific here. Should I, from current slide? Yes, so Jawad Boukashour is the team leader. Amina El Yagoubi is a mathematician, and Mohamed is an engineer and computer scientist. And together they have programmed an algorithm with matrices of sets for the purpose of a logistics application. So yes, they have coded something. My starting point was, because I was wondering, is it crazy to say you program a set? So starting with Lisp in mind, Lisp is, after all, a language where the primitives are lists, and a list, well, a set is a list with no order. So if you can do a list, you can do a set with Lisp. That would be my shortcut. However, of course, it's not that complicated to define the programs, because the formulas themselves are quite algebraic, and our colleagues Jawad and Amina and Mohammed have done it. So I can put you in touch with them. Maybe I can show.
Have they programmed in a functional language then?
Yes, yes,
okay.
yes.
In Lisp specifically.
I'm not sure about
but anyway,
the
functional style.
implementation. Yeah, very good question. After all, we are at BCS. Computing is about programming as well.
Well, it might make an interesting project for an expert in Mathematica or MATLAB to see what could be done for a library.
Yes. Exactly. And can I turn the question to you? What do you think of collaborative filtering with matrices of set? Is it something you see as promising or not?
Well, it could be. I mean, I'm not an expert in that area, but if it's a suitable way to model what they're trying to do, I don't know how do they model things at the moment with matrices, but not.
Yes,
sets.
just with numbers. Yeah.
It's purely MATLAB. Things like that, MATLAB.
Yeah.
Right.
I have a question here from Charles at the Met Office. It says, my maths is challenged here. However, I would be interested in any views as to where and why you may use an approach with multi-dimensional arrays versus matrices of sets.
Yes. So multi-dimensional arrays. So right now, of course, you have the three-dimensional aspect of fluid mechanics, for instance, and you add time to it. So you have a four-dimensional tensor, in fact. And the question could be, your tensor of objects which finally are replaced by numbers, because you speak of vectors, you speak of tensors, and then it's all relying on linear structures. Could you replace the elements by sets? And could you replace the number by sets? And you could create arrays of sets. That's probably one of the questions.
Okay, I think, should I say, and unless there's any other points anyone wants to raise.
There is Abdelatif, he has a question.
I beg your pardon, sorry.
I had a comment or remark here. My MATLAB coding was 20 years ago, but my memory about MATLAB is mainly about matrices, and all the data structure here are matrices. So it will be perhaps difficult to illustrate the concept here of matrices of sets with MATLAB. It will be, you have to do some gymnastic and, and some jungle with it. So it will be a bit difficult. But perhaps it has evolved. Perhaps there is other languages that are more suitable to directly illustrate this concept of matrices of sets.
Yeah, thank you, Abdelatif. And thank you, Charles. That's a very good point, the multidimensionality. So we have flattened the world with the matrices of sets, and a matrix is an image as well. is line column. So you can also say this is a generalization of the image processing. And instead of pixel, which is a vector of color RGB and probably other light parameters, but defined ones, you add in the image heterogeneous information, which can be metadata, which can be anything. So you could do steganography, you could hide information in the image, you could do cryptography with matrices of sets. And that is something I have not been able to investigate myself, but I'm convinced there may be possibilities there. And we see. Thank you, Charles. Yeah. Keith, back to you.
You're muted, Keith. Keith, you're muted.
Yes. Okay. Sorry about that. It's brilliant. It's a catchphrase, these, isn't it? You're muted. Okay. Well, everyone, if you'd like to, thank you so much for now. And if everyone would like to unmute themselves and just show our appreciation,